Let me see.
Hello, everyone. Welcome. We have a full house in person, and we have several people on Zoom. I'd like to introduce Zhihui Gao, who's a final year PhD student at Duke, co-advised by Professor Tingjun Chen and Professor Yiren Chen. His research interest is the next generation of wireless network systems, especially for in-physics computing for machine learning, spectrum sensing, and integrated sensing and communication. His work has been published in several conferences. I'm not going to list them all. So welcome.
Yeah. Thanks, Rajesh. Thanks, everyone. So this is Zhihui at Duke. Today, I'll just present the seminar topic at wireless in physics computing architecture using frequency mixers for deep learning at the edge. So over the years, we know that machine learning on edge devices is a very important topic. That is, the machine learning can be just a formula like this. That is, for example, we have a drone here as an edge device. And here we want a machine learning model, or we can always label it as W in blue. And also here we just assume that we have a camera on the drone so that it captures a image such as a cat here. So this image can serve as the machine learning input labeled as X in red. Then using this machine learning model, we can just do the machine learning inference so that we'll have the machine learning output. That is, the drone just recognize it as a cat. So this is a machine learning process on the edge. And over the years, we know that machine learning model size increases over years, like most recently it can be a billion or trillion parameters. So here, there are many solutions to overcome these machine learning on edge devices. That is, for example, we can first do some machine learning model optimization. For example, some quantization or pruning on the machine learning model to make the machine learning model smaller so that to reduce the computation cost. A second thing that we can just design some specific hardware acceleration, for example, accelerator, for example, ASICs, that is just use some digital computing for some specific machine learning model with a dimensions so that it can be the inference can be accelerated. The third way is that we can just use some efficient computing paradigm. For example, the in physics computing are known as analog computing. That is, the computing is essentially happens on the analog so that we can have many benefit. So in this presentation, our focus will be the third solution. So let me first introduce some popular efficient computing paradigms. First of all, we know that we have the in-memory computing, for example, RAM or some other things, memory stirrs. So here, for in-memory computing, the thing is that we do not need the memory access. This is because the in-memory computing directly happens on the memory. For example, we have X1, X2, X3, X4, and we just put the weight matrix on the persistent values so that the output Y1 to Y4 directly becomes the machine learning, the computing results. Since we know that the circuits can be implemented, fabricated in a very large scale, so that these in-memory computing can be implemented in a very large computing scales. For example, up to thousands or even tens of thousands of elements in the products or matrix vector multiplication. The other solution is optical computing. That is, we have some modulators, some optical components, hardware that, for example, the modulators, some WDM, we have fiber things, and we can just put X1, X2, X3 on different wavelengths and to modulate it with different weights. And on the receiver side, we can just use some integrators so that the Y1, Y2, Y4 can be obtained from these as an integral over time. So that this optical computing, we can just, it achieves extremely low energy consumption. And also this can be done in very high speed That this is because we always have very large bandwidth on the optical spectrum. In our case, we are aiming at a new computing paradigm. That is, first we just introduce the overall model, that is model disaggregated learning. So here we just consider a machine learning model that is originally deployed on a cloud server, that is on remote. Then we have multiple edge devices, for example, a lot of a swarm of drones over the air. And one drone can just capture a machine learning input, capture an image of a cat as the machine learning input. Then it just wants to use the machine learning model remotely on the cloud server to generate the machine learning output, Y as a cat. So the first method is to upload the machine learning input to the cloud. That is, each drone has its own, each drone has its own machine learning input that is different image captured by their own cameras. Then what they'll need to do is they just upload these images to the cloud server. And then we just do the machine learning inference digitally on the cloud server. This method is unscalable for edge devices number. This is because each drone need to upload their image in serial. That is, they just consume different spectral resources. And also it raises a privacy concern. That is, these images can be of a privacy issue. That is, some of the drones may not want to just upload their machine learning inputs, their own captured images. A second way is to download machine learning model to the edge. That is, this cloud server just broadcasts the whole machine learning model over the air, and seeing the machine learning model is the same for all of these edge devices, so that we only need to broadcast this model once. So in this way, we can just perform the machine learning inference on the edge devices here, so that the machine learning input can be do not need to be uploaded here. However, the shortcoming is that we have limited computation resources on the edge. Since here we'll need to do the inference on the edge. The other thing is that we'll need to store the whole machine learning model on the edge, which requires large storage. So here, the solution is we just do the machine learning inference directly on the radio frequency or in analog. The thing here is that we just do some encoded waveform for machine learning model W. Then we can just use some interesting or useful hardware or existing hardware components on the edge devices, so that when this hardware receives the machine learning model waveform, and it can also do the machine learning input on the other port, and this hardware just perform the analog computing, and the output naturally becomes the machine learning output. In this way, we know that the machine learning is done in analog on some specific hardware components on the edge devices, so that there's no need for computation cost on the edge devices. And also, we know that this machine learning model is broadcast over the air. And this is the same for all of these edge devices, so that it is scalable for edge devices number. That is, any edge device can do the machine learning inference at the same time upon receiving this machine learning model. And also, the edge devices do not need to upload the machine learning input to the cloud server, since everything is done on the edge. And so there's no need to computation, and the computing is directly occurs during receiving this machine learning model, so that there's also no need to model storage. So here the question is what's these mysterious hardware components? Here, we just want to use the frequency mixers. So what is the frequency mixer and how it works? Conventionally, a frequency mixer is essential hardware components on any edge devices for the internet access. For example, conventionally in communication, we have kind of baseband signals to be transmitted, and we want just to move this signal to the radio frequency to be broadcast over the air, so that we'll need to generate a local oscillator that is kind of frequency, that is kind of tone signal as a 2.4 gigahertz for Wi-Fi, or some other frequency for 5G is a very popular. So here, the thing here is that when we are doing transmitting, the baseband signal is up converted to some radio frequency to be transmitted. And on the receiver side, if we are receiving some frequency, we are receiving some waveform or signals at radio frequency, we also need this frequency mixer to down convert the frequency of the received signal to the baseband, so that we can just analyze it in some later on digital computing processors. In our system, what we want to do is that we just use the machine learning model to be wirelessly broadcast. Then the local oscillator that is originally generated by the edge devices is replaced by the machine learning inputs. In this way, the machine learning outputs directly becomes the machine learning the output waveform directly becomes the machine learning outputs. So let's zoom in to see how exactly this frequency mixer works, or how to formulate the computing process. So here we can just see this is a zoom in version or diagram of the frequency mixer. That is, we have one input as labeled as SY of t as the output, two inputs labeled as SW or SX of t. So here, according to this diagram, we can know that the output Sy of t is essentially the element-wise multiplication of Sw of t and Sx of t. This means, according to our signal processing knowledge, this corresponds to the linear convolution in frequency. That is, we all know that the element-wise multiplication in time is a linear convolution in frequency. So that in the frequency domain, if we have two spectrum of SW or SX of f, the output becomes a linear convolution between these two spectrums. So what is our radio frequency computing algorithm? So here we just consider a matrix vector multiplication between a matrix W, vector X as the input, and the vector as the output Y here. The core idea is to map W in this way, X in this way. So here, if we want to do the linear convolution between this vector and this vector, then we can just say when we have an offset like this, then we can just say, okay, a W00 aligns with X0, a W01 aligns with X1, and so on, so that the summation of these three things becomes the exactly Y0. And when we have offset like this, that is push all the X to the right by one grid, then we can just say, okay, now we have W10 aligns with X0, W11 aligns with X1, and so on, so that the summation of these three things becomes Y1. So that putting these two things together, we can just say, okay, the linear convolution of this vector and this vector becomes this, where among all of the output vectors, we notice that the middle two tones here becomes essentially our machine learning output. The other thing is that how to deal with the wireless channel distortion. That is essentially if we want to have if we have a matrix weight matrix like this, and we are to broadcast on a cloud server, then will this broadcast signal or here suffers wireless channel distortion, so that we can just label this distortion as H0 or to H12. Then the outcome, the received signal becomes element-wise multiplication between the wireless channel and the transmitted signals, so that everything becomes distorted, and eventually the Y1 and Y0 and Y1 becomes incorrect. So here, the thing we wanted to do is that we just put an encoding process here on the cloud server, so that the essentially it is not transmitting W, but transmitting some precoded vector of V. On the we can just say, okay, V is just a element-wise division between W and H. In this case, the received signal becomes exactly W. That is what we want to be received. Then this just go through the same process of what we have mentioned before. Then eventually we have a correct output Y. So when we have multiple devices, we also have two branches of wireless channel calibration. For example, we can first do the precoding process on the cloud server. That is, when we have different channels on different edges, we can just do an average across all of these devices. Then just apply in mean of these channels and do the inverse on the cloud server. In this way, this is what we have mentioned in the last slides. That is also a more efficient one. We can know that in this case, we do not need to do any computation on the edge. However, here we are average over different channels, and the channel calibration becomes a little bit coarse. The other way is just to do the channel calibration on the edge. That is, each devices can just apply their own wireless channel. In this way, we know that we'll need to introduce additional computation cost on the edge devices, so that it incurs more energy consumption, while it can achieve better channel calibration, since the applied channel edge is of their own. So in my presentation today, I'll just focus on this method, and the results of these these channel calibration on the edge devices can be found in my paper. So this is the overall computing architecture of my work. That is, we can just say, okay, we have one cloud server, we have multiple edge devices, and this cloud server has this deep learning model weight. And here it is broadcasting everything to the air, and all of these edge devices can receiving this broadcast signal can just do the machine learning inference at the same time. And here we zoom in to the edge devices. We can just say, okay, we have the vector of input vector. So this input vector just goes through some DAC, becomes some analog waveform. And this waveform is mixed with the received waveform wirelessly, going through this frequency mixer. And then it goes through some low pass filter, and to get the middle two things here, then go through the ADC, and eventually we have some IFFT-based decoding process. Eventually, we have this output vector. So over one loop here, it just performs a single matrix vector multiplication. And if we want to do multiple matrix vector multiplication in a machine learning model, then we just need to repeat this loop over and over again. So that eventually, when we have an input image here, we can just repeating this process, and eventually we'll have the predicted results. This is the experiments set up on a software-defined testbed. So here we just implement our everything on USRPX310 SDR as our transmitter and receiver. And here we can just see, okay, this is the transmitter, and this part is our cloud server that is broadcasting the pre-coded thing V here. And over the wireless channel, we have 3 edge devices, 1, 2, 3, with the 3 antennas here. And also we have 3 things, 3 devices here, and 3 frequency mixers here. And over the wireless channel, what we received becomes the W here, and going through this frequency mixer and mixed with the machine learning input X, we have the machine learning output Y received by this port. So this is a spectrum of example spectrum of W, X, and Y. And here we just put deep learning model W on 915 megahertz. That is open access ISM band. And then we just put our deep learning input X here on this peak. And eventually what we have is the the Y here as the mixed output at 0.285 gigahertz. So this is a zoom in version of how we do the experiments. That is, if we want to do a inner product between A and B, 4,000 points, then this is a spectrum we measured here. And when we zoom in this spectrum, we can just see, okay, we have a total of 4,000 tones here in the frequency domain. That is, the first tone corresponds to B1, the last tone corresponds to B4096. And similarly, we also have the same thing for the A. That is, we can see, okay, we have this spectrum here. When zooming in the whole spectrum, we have 4,000 tones here, with the first tone as A1 and last tone as A4000. And both signals are going through the frequency mixer here. And the output becomes a spectrum like this. When zooming in the very middle point, we can just see, okay, this tone becomes the thing of our inner product results. And the amplitude becomes the value of C here. So this is a general purpose computing accuracy results. That is, we just consider endpoint inner product from C equals to A and B. That is, we have 2 spectrum here. So when I just various different SNR, and the blue one is simulated results over, this is SNR versus computing accuracy in bit. And we just show the simulation results and the experimental result. And here we can just see that, okay, the simulation is very ideal, that we can just increase the computing accuracy as we increase the SNR. While for the experiment things, because of the hardware imperfection, so that the computing accuracy is somehow saturated around 5.5 bit. However, this 5.5 bit computing accuracy is overall good enough for deep learning inference process. We can just zoom in the results of 15 dB SNR, and I just put the analog computing and the analog computing and digital computing results here. We can just see, okay, they fit like this. And if we increase SNR to 25 dB, then it becomes thinner. That is more ideal. And also, I tried N up to 32,000 inner product element in the products, and we can see that the performance is very close to what we have at 4,000. So that this means our experiments can support the state-of-the-art machine learning inference request, including large language models. That is, can only up to 10,000. And also, I'd like to analyze the energy efficiency. So this is the energy matrix vector multiplication of our case. And here, I just label this dimension as M, this dimension as N. So this is our diagram on the edge devices. here, we know that the frequency mixer is passive, the low pass filter is passive, the antenna is passive, and all of the energy consumption comes from the DAC and the ADC and decoding part. And I just list the computing energy complexity here. That is the energy for the whole matrix vector multiplication of a conventional digital computing is OMN, since it involves M times N multiplication and addition. And if we normalize everything to the number of max, then the conventional digital computing becomes O1. In our proposed radio frequency computing, we can just say the DAC is actually K times M times N, where K is greatly smaller than 1. We can just somehow ignore this term. And for ADC, it only needs to capture two things for Y0 and Y1, so it is only OM, and normalized by M times N, it becomes O1 over N. And this is the same for the decoding part, so that eventually the total energy consumption becomes O1 over N, which is largely, complexity, which is of much smaller complexity than the conventional digital computing. So here we just do the experiments and to measure everything here. And the x-axis of this plot is the input size n, and y-axis is the energy per Mach in a log scale. And here we can just see the experimental results of this orange line. This orange line is total energy, and we can just see, okay, in the very beginning, when we increase the input size, the energy per Mach just reduces following a trend of 1 over n. And when we have an extremely large input size n here, it will be saturated by the first term of E DAC. And in comparison, the state-of-the-art digital computing can be 1 picojoule per Mach, that is here. So that comparing this gray line here and the orange line here, we can just see, okay, our system achieves 2 to 3 orders of magnitudes lower energy consumption. So this is a fully analog model with logistic regression. That is, I just put an MNIST input here and use a 7, 8, 4 to 10 matrix vector multiplication. So this is the spectrum. This is a waveform of the input corresponds to this input. And this also, this is a weight corresponds to the machine learning model. And this is a spectrum of the digital input of these 4. And after the frequency mixer, we just go through this is a frequency mixed results. And after going through the low pass filter, we just use a spectrum analyzer to receive everything. And eventually the output becomes a 10 by 1 vector here. And if we have highest things on 4, then it means this input image is predicted as 4. So this is our demo. I'll just show the video here. So this is our input channel X here, and this is our weight matrix here. And we are doing wireless things. And this is our transmitting antenna. This is receiving antenna. And this is our spectrum analyzer that is as a receiver to receiving Y equals W times X. So first, we just want to transmit X as digit 4. Then the two lights are on so that we can just say, okay, the computing is now in progress. And this is what we received on the spectrum analyzer. And we can just see we have a total of 10 tones here. This is 0, 1, 2, 3, 4. And here 4 is the highest, which means the digit that image is predicted as digit 4. Then we can just change to another image, say digit 1. Okay, in this case, we can just say, okay, the second one, that's 0, 1, the second one becomes the highest. And also we can slightly tune these two antennas so that we can see the received signal just change a little bit. Okay, so next we further consider the three fully connected layer model on MNIST dataset. That is, we have three fully connected layers or three matrix vector multiplications from 784 to 300 to 100 to 10. So over different layers, since everything is in complex value, so that we just consider that of true phase as the activation function. And in this network, we have a total parameter of 266 kilo, while the total number of max, that is 1 million. And in digital computing, we can just achieve a digital accuracy of 98.1%. And the confusion matrix is like this. And for the multi-layer model on our system, we can just I just show one example here. That is, one image is going through this part, and the weight becomes this, the input becomes this, and everything goes through the low pass filter, then go through ADC. And ADC just sample things here, this point, this point, this point, and going through the decoding process, and we have the output of the first layer. Then the first layer goes through the activation function, and it becomes the input of that second layer, and repeating again, and eventually we have the output of the third layer. That is a 10 by 1 vector, and here we can just predict it as 4 if the fifth bar is the highest. Then the results is shown here. That is, we just consider the trade-off between the energy per Mach and the classification accuracy. And here we can just look at the digital computing accuracy is this dashed line. And I just show the breakdown of EDAC, EADC, and E-decoding. And for this point, I just zoom in everything, and we can just say, okay, we have the energy per Mach as energy per inference as 6 nanojoule, and energy per Mach as 6 femtojoule. And our analog computing achieved a classification accuracy of 95.7% comparing to a digital computing of 98.1%. They are very close. I also tried a 3 fully connected layer model on audio MNIST dataset, that is a speech recognition dataset. So this is a waveform of spoken to, and we just put it through a short time Fourier transform into a spectrogram here. And then I just treat it as an image, and I do flattening, and I just put it into the same model architecture. So here the difference is that this time we have 4,000 elements as the input, so that the first layer becomes much larger than the last one, so that the number of parameters in this model becomes 1 million, and the number of max becomes close to 5 million. And this digital computing accuracy is 99.2%. So this is our results on the audio MNIST dataset. And here we have the digital computing accuracy on this gray dashed line. And we just vary different energy consumption. And we have the simulation, the experimental curves for EDAC. And we also have the dashed line for EADC and E-decoding here. And summing these up, we have the total energy in this line here. That is the energy of the total of our system. And here we just zoom in this point here and put it here, and we can see, okay, since the model becomes larger, so that the energy per inference is 13.69 nanojoule. This is slightly larger than the previous one, while the number of the energy per Mach is reduced to 2.78 femtojoule. That is, we can just recall the energy per Mach of digital computing of 1 picojoule per meg, and we can just say, okay, this is more than 2 or close to 3 orders of magnitude lower than that. And under this low energy consumption, we can just see that the classification accuracy on our scheme achieves 97.2% classification accuracy, comparing to digital computing of 99.2%. We only have 2.0% classification accuracy degradation, which is good enough. So in summary, this is in one word is that I just developed a discrete in physics computing architecture uses radio frequency waves and mixers for deep learning at wireless edge. So this is our cloud server. I just want to remind everything again. So here in my work, I have a cloud server here that is broadcasting the machine learning model weight wirelessly. And any edge devices or multiple edge devices can receive these broadcast weights, so that for the machine learning inference, then we can just use a frequency mixer here that is fully passive, which mixes the machine learning input here and the weight here, and the output essentially becomes the machine learning output here. If we want to do machine learning for the whole deep learning model, then we can just repeat this thing over and over again so that we can have the machine learning output. So this is all I want to share today, and the corresponding paper is on the submission to Science Advances. And thanks to my Professor Tingjun Chen, and also thanks to my collaborators in MIT. Thanks. Is there any questions from the audience?
So we have a question online.
Yeah.
Can you please define computing accuracy?
Oh, yes. Okay, so this is a slice of the computing accuracy. So here, what we did is that we just normalize the inner product result, C here, within -1 and +1. So in this case, most of the C here between a range of 2. So that here, my definition of computing accuracy is that we just say the IMSC here, 0.099 divided by 2. Then I just take a log 2 of this whole thing and take a negative. Or we can just say, since the largest range is 2, we just say, okay, 2 divided by this number, and we take a log 2. So here we can just say, for example, if the RMS is 2 to the -3, then it corresponds to computing accuracy of 4-bit. This is because 2 divided by this number becomes 16. Then take log 2, it becomes 4. Then we have same thing for the this one and this one. Yeah, thanks for your question.
Okay, so I have a good question for let's say in the future you want to deploy some transformer-based GPT-based models. What people will be major difficulties is?
Oh yeah.
Why don't you repeat the question so that people online can hear?
Yeah, so the question is that what's the major challenge if we want to deploy a transformer in our system? Right. So here the answer is that the major challenge is that the transformer typically requires a very high computing accuracy. So for example, the 5-bit computing accuracy may not be enough, and also the transformer can be very deep. For example, Llama 7B can have tens of such a transformer architecture, so that these and the computing error can be accumulated over layers and layers, so that maybe you will need to increase the computing accuracy to a higher level to make the error will not be accumulated over layers.
Another question online. How are you modulating your weights at cloud into the wireless signal?
Oh, yes, that's
DM.
yeah, that's a good question. So I'll just yes, the quick answer is yes. So here, the thing here is that we just modulate this weight. We just put the elements of weights here in this form, and we can just say, okay, this is a subcarriers on the OFDM, and essentially we just perform the FFT that is exactly the same as OFDM to convert this frequency signal into time domain. And also we have the same thing for the X input here, and we have the same thing here, and we just perform the FFT to convert it from frequency domain to time domain. And eventually to decode thing, this decoder is actually an OFDM decoder that is conduct IFFT, converts these frequency domain Y1 and Y0 into time domain. Can convert the time domain Y1, Y0 into frequency domain, and where we can extract things here. Yeah.
Any other questions?
So one more question. So regarding, you mentioned something about the propagation error when we're dealing with larger or linear network. Do you think increasing the bit resolution for that ABC will be able to solve that problem, or is it not solvable?
Oh yeah. So that audience, yeah, just asked that whether the good computing accuracy of DAC or ADC can resolve the accumulated error. It's just a follow-up question of the last question. So that the answer is not really. Actually, no, since somehow for now the computing accuracy is not bottlenecked by the DAC or ADC. Since here, our system we are using USRP X310 SDR, and the DAC or ADC can be a resolution of 12 or 14 or 16 bit, while our computing accuracy is mainly bottlenecked by the noises or some hardware imperfection. This means, and eventually the computing accuracy is only 5 bit, so that the DAC and ADC are not the bottleneck for now. But if we are, say someday we can improve the computing accuracy to say 10 bit or higher using a better hardware or some better techniques, then these ADC and DAC can be a bottleneck.
Okay.
Yeah. Thanks.
Any other questions? Online? That's it. Thank you very much.
Yeah, thanks everyone.
And thank you all for joining.